Recording in progress.
Traffic intensity parameter. So for MM1, S was 1, so we needed lambda over mu to be less than 1, which means lambda less than mu. So everybody remember what is MMS system? So it was, you have the states 0, 1, S, S plus 1, and so on. Arrival rate is always lambda. The service rate, if there is one customer in the system, it goes to one server, and you have a service rate of mu. If you have S customers in the system, S customers go to S different servers. So you have a service rate which is S mu and 2 mu and so on. After S, if there are S plus 1 customers in the system, S of them go to the servers, so your service rate remains S mu. Does it make sense for a MMS system? We can write the steady state equation like we did for the birth and death process. We could solve them. If there is a finite capacity, you will also have, based on the n, last equation, which basically has is will be different, like we did for MM1 with the finite queuing capacity. So we can have all those type of additional changes. But let's consider the standard MMS system. So what we'll do is we'll give you the formula of LQ for different S. So S, okay. For S equal to 1, which was the case we did in the last lecture, it is rho square upon 1 minus. Just for recalling, rho is lambda upon S times mu. So for the first case, rho is lambda upon mu, and we did that expression last time, and which can be verified. For S equal to 2, this expression becomes 2 times rho cube over 1 minus rho square. For 3, it is 9 times rho 4 upon 2 plus 2 rho minus rho square minus 3 rho cube. Any questions for these expressions?
How are you getting these expressions?
Okay. So the way we get these expressions is you first solve all those. Okay, I'll tell the approach, but we are not going to solve them. Um, the approach is standard, which is you calculate all the pi n's for the steady state, solving the limiting equations. Then you calculate L, which is summation n pi n equals 0 to infinity. Then you get W as um, L divided by lambda, right? Then you get WQ, which is W minus um, expected service time, which is 1 over mu. And then you calculate LQ, which is lambda times WQ. So that is the method to solve all this. And we gave you the expression of pi n's for MMS system. And as you recall, they were actually complex to do all these summations, which is why we directly gave you the final results.
Okay, thank you. So for the exams, they would be on this table, so we would have the formula.
Yes, yes, that's
Okay,
the purpose, that you can directly use the formulas.
thank you.
Um, there is one error I made. Just 1 second. So WQ. No, I think this is fine. So so now you have LQ from the expressions. If you want to calculate the remaining expressions, you will do the opposite method, which is WQ is LQ by lambda. If you already have the LQ expressions, you can calculate from there the WQ expression. Then you can calculate W expression as WQ plus 1 by mu, and L expressions as lambda times W expression. So given that you already have LQ expression from the table, you can calculate the rest using these formulas. Does this make sense? Any questions here? So let me ask next question. So consider a MM2 system with arrival rate lambda and service rate of each of the server as mu. Since there are two servers, each serving with the rate of mu, let us compare that system to a MM1 system with arrival rate lambda but service rate twice mu. The reason I'm doing twice mu is in the first system, there were two servers, each serving at a rate of mu. So, in order for a meaningful comparison, I have to do MM1 system with a server serving twice as fast. Does it make sense that these two are reasonable systems to compare? So, what is happening is in the first case, I'm having two people who are serving the customers at the rate of, let us say, 1 per hour each. So, two customers are served per hour. In the second case, I'm taking twice as efficient person who can resolve a customer in half an hour, which again means I can process two customers in an hour. So this is basically, do I get more less efficient people or less more efficient people? So the first is more people serving less efficient who can serve only at the rate of mu, or I get one person who is actually twice as efficient. So the question is essentially these two are comparable systems, but which is better? What do you think? Which is better? Should I get a more efficient person or should I get two less efficient people? Basically, more people or faster people? Right? Why is that? You can name that, but right. Assumptions too. Let's think about it more. I mean, the question is ambiguous. Um, so the ambiguity in the question is I did not tell what better means. So, what do you think better means? We give you the matrix L, LQ, W, WQ. What does better mean? Which metric would you think to answer this question out of those four? And the interesting thing is, metric changes the answer of which is better. So, if you were going into the Starbucks queue, what would you care about? Which of those four metrics would you care about? Anyone? Would you care about L, W, LQ, or WQ?
I would guess WQ just because
Okay.
that's how long the customer would spend waiting in the queue. So if you
Mm-hmm.
decrease that, then they're gonna at least get to the front of the line and get served quicker, which would be the goal.
Served quicker or not is still a question mark, right? Because you have less efficient in one case and more efficient in one case. In one case, you will spend more time with the server. In other case, you will spend less time with the server.
Oh, I guess
So,
yeah, I guess that makes sense. Okay. Even though
right. So
they're
this
two
that's why W and WQ becomes important. Which is better, right?
oh,
Because
huh.
it. So, do you care about W or WQ? That is essentially, of course, L and LQ are only proportional lambda times, so it doesn't matter. So W or WQ, what is more important? From in the Starbucks to getting out of the Starbucks, or the amount of time you spend waiting in the queue without getting to the person? And that's an interesting question. Many people think it is, I don't care how much time I take with the server, at least I'm there being served, and they hate the time they are waiting in the queue for something else. So for many people, it is WQ. But of course, if you're short on time, you have to go to another meeting, then it's not the WQ, it's the total amount in the system that matters. So it depends upon the mood of the customer and the mode of the customer in which they are entering the system. So better depends upon which definition we choose. So let us start with the definition of WQ. Okay. So which has better WQ? So let us compare them. So we are comparing WQ, and I'm putting the two options. First is MM1 with 2 mu, double the service rate, and second is MM1 with mu. In both the cases, rho is lambda upon 2 mu. Here also, rho is lambda upon 2 mu. So the reason is essentially rho was lambda upon c times mu, and sorry, mm2 at right. Okay, c or s, it was mmc. So rho was lambda upon s times mu. S is 2, so that's why the 2 came here. Here it was lambda upon mu, but the mu here is 2 mu. Okay. So rho is the same in both cases. So let us then write the LQ expressions for both of them from the table. We had the table. Um, you can copy the expressions. I think I can from. So LQ in this case was rho square upon 1 minus rho. Here it was 2 rho cube over 1 minus rho square, which is rho square upon 1 minus rho times 2 rho over 1 plus rho. Mhm. So rho is smaller than 1 in both cases. Otherwise, the system is not stable. So if you have to compare this, so let us call this system 1. Let's call this system 2. 2 rho upon 1 plus rho. Is that smaller than 1 or bigger than 1? First, do you understand how we got from here to here? I just took the rho square over 1 minus rho common. In the numerator, it was 2 rho cube, so rho square times 2 rho. In the denominator, it was 1 minus rho square, which is 1 minus rho times 1 plus rho. Right? So now, is 2 rho over 1 plus rho larger than 1 or smaller than 1? If rho is less than 1. So in both cases, WQ will just be LQ by lambda. So comparing WQ or LQ is actually the same. Okay, so 2 rho over 1 plus rho, less than 1, greater than 1.
Would it be less than?
Less than 1, of course, because 2 rho is rho plus rho, and rho is less than 1, so the numerator is less than the denominator. So this is less than LQ1. So that essentially tells me that MM2 system has a, and as I mentioned, WQ for both system is just LQ by lambda. So if I'm saying LQ is better, that means WQ for second system is also better. So this also gives me WQ for second system is less than WQ for first system. So what it tells me is two less efficient servers are better for me. Does this make sense? Is it intuitive? Not intuitive.
Did you just say two less efficient servers are better?
Yes, that's what the formula said, right? WQ for the second system is smaller.
Why is LQ bigger for the second system?
Where did we say bigger? LQ for the second system is smaller than LQ for the first system, right?
Oh, okay.
So waiting time in the queue for second system is smaller than waiting time in the queue for the first system. So having two servers at the rate of mu each is better than having one efficient server who was serving as double the speed. So if people care about just the waiting time in the queue, have more less efficient people to serve you coffee. We are assuming equivalence in a way that the double the efficient person will also charge double the salary, so you are actually paying salary based on the service rate. So in the second case you are paying two people each based on the rate of mu. In the first case you are paying one person at the rate of 2 mu. So in terms of cost they are similar, and you were comparing one more efficient person versus two less efficient people. And what we showed is it is better to hire less efficient people at lower salaries. So if you're a system designer or a person thinking of how to who to hire and how to run your system, these things become important of what might people care about, and based on that, what metric you be choosing. Any questions for this before we go further?
Does this change if it's not a memoryless case? Like if you're
Yes.
to consider, okay.
Yes, everything will change. The formulas are no longer valid. Formulas are only valid for memoryless case.
Gotcha.
So let us see now what if the metric is W? Does our answers change? So we have to compute W. W is it L divided by lambda or L times lambda? Which direction does lambda go? L is lambda times W. So W is L by lambda, but I think we are not going to W anyway. L. So W is WQ plus 1 by mu in both cases. WQ is LQ by lambda plus 1 by mu. So I want to bring everything in terms of rows. That's why I'm basically taking 1 over lambda out. This is LQ plus lambda by mu. So times 2 times 2. Any questions so far? Continuing further, this is 1 over lambda times LQ plus 2 times rho in both these systems was lambda over 2 mu, as we said in the previous slide. And the reason I did this calculation is so that I don't have to bring in lambda mu's. Since lambda is a constant, comparing W is same as comparing LQ plus 2 times rho. No, I think I made a mistake here. Sorry. So ignore this so far. So let us compare the two systems. First was MM1 with 2 mu, and second was MM2 with the mu. We know the LQ formulas for both of them, which was in the table. So WQ we already know was LQ by lambda. WQ was LQ by lambda. What is W from WQ here? WQ plus what? What should we be adding here? So time waiting in the queue plus how much? What do you think I should be adding here? 1 over the service rate. How much is the service rate here of the server? How much is the service rate?
Is it 2 mu?
Yes, it is 2.
I have a
And in this,
question about lambda. Sorry. Is lambda the same for MM1 and MM2 because it's just the rate of customers?
yes, lambda is the same for both. That's why I haven't written them.
Thank you.
So, okay, in the second case, W is WQ plus what? One over service rate. What is the service rate here? What is the service rate?
Is it 2 mu?
No, you go to one of the server,
So just mu.
just me. And that is where the difference comes. So even though WQ was smaller, the term that you're adding is bigger in the second case than in the first case for the waiting time, right? Because in the second case, you spent less time in the queue, but then you spend more time with the server. In the first case, you spend more time in the queue, but you spend less time with the server because the server is faster in the first case. Does that make sense? Okay. So now we are trying to simplify. This is LQ by lambda plus 1 by mu, which is 1 over lambda times LQ plus lambda upon 2 mu, and lambda upon 2 mu is nothing but rho. In this case, W is LQ over lambda plus 1 over mu which is 1 over lambda LQ plus 2 times lambda over 2 mu, which is plus 2 times. So you're spending twice the amount of time with the server in the second case than in the first case. Any questions in these calculations?
What exactly is this p-value that we're writing down?
Oh, this is the rho value. It's all rows, there's no p. Rho is that lambda upon 2 mu in these cases.
Lambda. Oh, is it always lambda over? Oh, okay, yeah. In that earlier. Okay.
Yeah, when we
We
did the
always
OQ
are just
tables.
going to plug that in.
Yes, means we made the row same for both of them. It was the same. It was lambda upon 2 mu. That's why I could compare with the same row.
Got it.
Because row in system 1 and system 2 is the same. Right. If that is clear, then we'll go at comparing these expressions. So this is mm1 2 mu and this is mm2 with mu. So we basically said W for the first system is 1 over lambda times LQ plus rho. And in this case, W for the second system is 1 over lambda LQ plus 2. Now, 1 over lambda I can ignore because I'm only comparing this is better or this is better. Okay. So, or I could say just L of 1 because I'm ignoring lambda. But LQ plus rho is in this case, LQ was what? For mm1, rho square upon 1 minus rho plus rho. In this system, I'm writing LQ plus 2 rho. LQ for this system was 2 rho cube over 1 minus rho square plus 2. Now these are the two expressions for W1 and W2 and I have to check which one is bigger. Let's simplify them. Let's take the LCM for both. 1 minus rho is the LCM, rho square plus rho times 1 minus rho, which is rho minus rho square. In this case, I take the LCM as 1 over 1 minus rho square. This is 2 rho cube plus 2 rho minus 2 rho cube. Any questions at these calculations? Is this clear so far? Does everybody see where the expressions are coming from? LQ expressions came from the table and rest came from previously. Okay, to proceed.
How did you know to factor out, how do you know when to substitute row in? For example, on the previous slide, we had 1 over 2 mu, and then you factored out a 1 over lambda, and then we just had row.
Yes, so basically means it's the same as bringing the units. So I knew LQ is a function of only row, and if I multiply this by lambda, then lambda over mu could be written as a function of row. So that was why I did the trick. But otherwise, you can keep in terms of lambda and mu. But only thing is, it just makes the expressions a bit messy. Row was just substituted for our simplicity. So it was the same even in the previous case of comparisons. We actually took out 1 over lambda. So let us see here. When we compared the WQ, remember that I compared with LQs and I just kept divided by lambda there. It's 1 over lambda was common even here in both the expressions when we would have to do WQs.
Yes.
So it's basically the same intuition that if I take 1 over lambda out, the other things could be made a function of rho.
Okay. Thank you.
Alright, so far so good. Then notice that rho square and rho square cancel out here. So this becomes rho upon 1 minus rho. Same here. 2, 2 rho cube and 2 rho cube cancel out. So this becomes 2 rho upon 1 minus rho square, which is, I again take the first one common, rho upon 1 minus rho times 2 over 1 plus. So numerator is 2 times rho, which is rho times 2. Denominator is 1 minus rho square, which is 1 minus rho times 1 plus rho. Is that clear? Any issues in these calculations? Right. Assuming that the calculations are good. Now this expression 2 over 1 plus rho, is that greater than 1 or less than 1? Rho is less than 1. If rho is less than 1, then 2 over 1 plus rho, is that greater than 1 or less than 1? Anyone?
It's greater than 1.
Yes, because 2 is 1 plus 1 over 1 plus rho, and rho is smaller than 1, so this becomes larger than 1. So that means this term is, since this is greater than 1, this term becomes larger than W for the first system. So what do you see here? If we care about the total waiting time in the system, including in the queue and in the service, then W for the first system is smaller, which means it is better to have one more efficient person than two less efficient people. So if I care about total waiting time in the system, then more efficient people are good. If I care about waiting time in the queue alone, then less efficient people are good. After doing all these calculations, does that make intuitive sense? So more efficient people will serve you faster, so you'll be out of the system from there faster. But of course, you'll spend a longer time in the queue because there is only one server. If there are two servers in the front, less efficient, you'll still spend lower time in the queue, but then you'll spend a lot of time in the service, which means that the overall amount of time you spend in the system is still larger. Any thoughts, comments, questions?
So the conclusion that we're supposed to draw here is that for in terms of for the entire queue, like what the waiting time for the entire system, I guess, including the queue and the service time, it's better to have one really efficient server.
Yes. Less, more efficient servers are better for total waiting time in the system. Um, more, less efficient servers are better for waiting time in the queue. So when I asked which is better, it depends upon what is the metric. Do we care about waiting time in the queue or waiting time in the system? Answer is not the same for both the metrics. For one metric, one is better, and for the other metric, the other one is better.
So then, as kind of like facility planner or like somebody making some kind of decisions about like how many servers you're going to have for your system, you would be basically analyzing like which would be more important, the time in the queue or the time in the system for your given context and how to balance that.
Yes, exactly. So you can have a optimization with the alpha times the first objective plus 1 minus alpha times the second objective, and then see what to do.
Oh, okay. Gotcha. You like
So
weight it
these
kind of, you weight it kind of to see like
you wait
how
kind
much do you care about either one.
Mhm. And note that in real systems, these servers may not really be people. They may actually be machines you might be investing in, right? Who might be processing your good. You have a set of jobs that will be done by machines in a queue, and this might be you use two um, like a GPU machines, for example. You use two cheaper, less efficient GPU machines or one more efficient GPU machine. Right. So it could be basically means Starbucks example is just one example. The computing example is actually the same queuing example because your jobs Your computing jobs do wait in a queue, and then you have basically the server or the processor that then processes the jobs. It's exactly the same queuing system, nothing changes. Right. So, yes, we are talking about servers here as people just to make things clear, but servers could just be machines.
Under the machine case, would the assumption of memoryless be more accurate to an extent or not
Okay,
really?
so we have done a lot of works in the area, so I can explain you what happens there. So it is basically not memoryless, of course, that is to be expected. But there is one distribution. So this is basically a real world case. Um, so the way we model it, uh, essentially, is basically there's a distribution which is called shifted exponential. This is the service type distribution. So what shifted exponential does is you basically have a constant shift plus a process which is an exponential. So think of it this way that you have a job. It will definitely take a constant time based on the size of the job and the processing time and everything. That makes sense, right? But then you have another memoryless behavior which depends upon background tasks, which basically are time varying, depend on the temperature of the system, and many other things. And if you actually model many of these jobs as a shifted exponential, it is much accurate representation than, of course, a constant or an exponential. Now, once you model things as shifted exponential, of course, the expressions that we did do not work, but some of the insights do actually carry forward because the way you analyze exponential is actually the same way. So that's why we actually try to get through the formulas, not just the formulas, but the insights of how things are going, so that if it is more general distribution, um, some of the some of the procedures you can follow, but not the formulas. So yes, to answer your question, real world is definitely not exponential. It is more general, but exponential is the basis for understanding so that you can then start proceeding further. We will go over some expressions, but there are different ways of formulating the system. So what we formulated was, remember we were doing M1 for now, MM, or we also did S, but let us focus on one for now. If you have a MG1 system where the service time is general, which is what is happening here for shifted exponential, you basically still consider the memoryless arrival, and the way you analyze is between the two arrivals what happens. So you still use the continuous time Markov chain, you rely on the first memoryless, and then analyze it as a continuous time Markov chain where continuity the memoryless part is on the arrivals. So things can still be analyzed beyond that, but this is an undergrad course and the first course for queuing system. So we keep it basically at the memoryless processes. Does that kind of answer your question?
You know, it does. Thank you for providing some insight onto that. It's really
Okay.
interesting how the exponential is used as a basis for modeling all of those things.
Right. And shifted exponential is a very common distribution that is used in the literature, and many of the results happen there. And it's easier because you can exploit exponential, and you can also model the real world characteristics. Mm. So, of course, remember this slide is not for the exams. This was just for insights. Okay. So, any further questions on this? All right, we are more or less done with the chapter. We are doing some extensions now. So, did you get the homework in Brightspace or not yet? Do you have the homework on Brightspace? Yes or no?
Not yet.
Not yet. Okay, but yeah, homework will be coming soon and it will only include the topics till now. Okay. So the next concept we are covering is bulk service. So bulk service, I think we gave this type of insight before, but what bulk service essentially does is it's like an elevator. Um, Elevator at a time. So think of you going in front of an elevator, and elevator has a capacity of, let us say, two people. So it can take up to two people into the queue and serve them. So essentially, if you have a bit more people, all those could be served together. That is basically what we mean by bulk service. So let's take an example. The server can serve next two customers. I'm taking two for simplicity. The mechanism can be extended to any number at same time. If only one customer line, then server services that customer. So it doesn't wait for the queue to have two customers. So again, service time is exponential with rate mu. Arrival rate for customers is exponential. Is the set clear? So we have to now set this up as a continuous time Markov chain. This is not in the type of system that we, and it's not a birth and death process. So even though we were doing birth and death processes till now, means this type of question is not birth and death. Why is that? In birth and death, that happens one at a time. Here, if there are 10 customers, two people will go together. From 10, you will go to 8. You will not go to 9. So it is skipping the immediate back. So let us first define the states and then go over the transitions. So in terms of states, we define a state, let us say 0 prime, as no none in service, which means let us say the elevator is empty, nobody is in the system. Okay. As soon as a person comes in, the elevator will go. 0 is there is nobody in the queue, but the elevator is going up. So the server is busy, but no one waiting. So we don't know whether there is one person in the elevator or two people in the elevator, but the server is doing the job. Nobody is waiting in the queue. So can somebody explain me? Okay, let me define next and then I'll ask the question. Then a state n is n customers waiting in the queue. So what I did was I defined the states based on the number of people in the queue, not based on the number of people in the system. Can somebody tell me why did I do that? Why did I define the states based on the queue and not based on the system? In the previous cases, we were defining the states based on the number of people in the system. In this particular case, we defined them based on number of people in the queue. Any thoughts? Anyone? Okay. Reason is if there are n people in the system, we don't know whether the elevator is taking one person or two people. So then I have to divide all the things about number of people in the system to the elevator carrying one person or the elevator carrying two people. That will basically double my number of states if I take the thing in the system. So I would have 10 people in the system, elevator having one person. 10 people in the system, elevator carrying two people. So since that will double my number of states, I define them as number of people in the queue because then I could basically then characterize from LQ and then go to L. Does that make sense? Now, zero people in the queue was another interesting thing. Even though there are zero people in the queue, we don't know whether the elevator is empty or it is already serving. So the state zero people in the queue had to be divided into two states. The server is busy or the server is not busy. All right, so let us try to make the transition diagram. 0, 9, 0, 1, 2, let's say 3. I made 0 prime. If an arrival happens, where do I go? If an arrival happens, where do I go? So I have 0 people in the queue. Elevator is empty. One customer comes. What do I do? Elevator should be taking that person out, right? So which state do I land up in? 0. Yes. If an arrival happens, I land up in this state. There cannot be any departure because I already have server is empty. Now I'm in state 0. If there is an arrival, where do I go? So I have nobody in the queue. I have the server who is elevator who is still going up, still serving the person. New customer comes. Where do I go? The new person has to wait in the queue because the server is busy. Given that the new customer is waiting in the queue, where do I go?
Would you go to state one for one customer waiting in the queue?
Yes. So you had zero people waiting in the queue, you'll have now one person waiting in the queue. So you have one person waiting in the queue, new arrival, you keep on going to more people in the queue. Okay. So let us now talk about services. We are in state zero. The server is busy, nobody was in the queue. If you completed your service, where do you go?
Zero
Nobody in the
prime.
queue. To zero prime. Yes. Now you are in state one, which means the server is busy and there is one person in the queue. If the server finishes, what happens? If the server finishes, this one person will go in the elevator. How many people in the queue? And the server will be busy. So where do you go? You had one person in the queue and server was busy. When the server finishes the job, this one person will enter the elevator and there will be zero people in the queue and the elevator will be busy. So where do I go?
State zero.
State zero. I'm in state two. You have two people in the queue. Server was serving. When the server finishes, then both these people will enter the elevator together and there will be nobody left in the queue. Both these two will be in the elevator and elevator will get busy. So where would I go from when the server finishes the job?
And we go to zero, actually.
Yes. Now I'm in state three. I have three people in the queue. Server finishes the job. The first two people enter service together. So first two people will enter elevator together. Given two people enter the elevator together, I will only be left with one person in the queue. Where do I go? All the way to one. Similarly, four will go to two, five will go to three, and so on. Does this make sense? So this is basically how my system of equations will be. I can write my steady state equations. So steady state equations are state rate leaving equals rate entering. State zero prime. What is the rate of leaving zero prime? What's the rate of leaving zero prime? Lambda is the only outgoing transition, so lambda times p zero prime. Rate of entering is this mu transition, which is mu times p of zero, pi of zero. So this is lambda pi zero prime equals mu pi zero. Now let's talk about state 0. State 0. Leaving is both mu and lambda. Entering here are three transitions. One from state 0 prime, one from state 1, and one from state 2. So when I write this becomes lambda plus mu by 0. Leaving are just 2, but entering are three transitions, which are lambda p 0 prime plus mu p 1 plus mu p 2. If I take any n larger than 1, larger than or equal to 1, let us say 2, you have two outgoing, one is lambda and one is mu, and two incoming. Two will enter from 1 or from 4. One will enter from 0 or from 3. So based on that, I can write it in general. State n for n greater equal to 1. You have lambda plus mu, which are the outgoing. Sorry, there is no p. All the p's has to be pi's. So this is the leaving and entering are lambda from the previous state and mu from the two future states. So these become my system of equations. Any questions so far? So anybody know what is difference equation? Have, have you previously done any difference equations? Yes or no? So the last equation that we have, where n is a function of the other states, that is called the difference equation, which is basically a discrete version of differential equations. So we have approaches to solve difference equations. With first two equations will become the corner cases, which can be handled. So we can actually solve all these type of equations. But since we haven't done solving difference equations in this course, we'll directly give the answers. And if you're interested, you can see how to solve difference equations. So the solution of these equations will be, let alpha be 1 plus 4 lambda by mu minus 1 by 2. Then p0 is lambda times 1 minus alpha over lambda plus mu 1 minus alpha. P0 prime is mu 1 minus alpha. Sorry, all these are all i's. Mu 1 minus alpha over same denominator, lambda plus mu 1 minus alpha, and phi n is alpha n lambda r minus over lambda plus mu 1 minus alpha for all n greater than equal to 0. So it also includes the previous 0. So this is the solution of the steady state equations. So given these expressions, we can solve LQ. LQ is easy for us because that is just n times Pn. Summation n equal to n times pi n. We already solved pi n now. So this summation could be just from 1 to infinity. So given that you have pi n in the previous slide, you can actually solve it because everything other than alpha to the power n is a constant that comes outside. So you'll have n times alpha n. Um, I think we will take that in the next lecture. So we'll complete this example given that there are only 2 minutes left. So the intuition is basically you have pi n, you can compute LQ from there very easily. Only thing n times alpha n, which we already did as alpha over 1 minus alpha square. So after computing this, you can compute WQ, then W, and then L. So that will complete the entire analysis of this example. So in the next lecture, we will continue this example. We will go a bit over MG1 formula, and then we will move over to next chapter, which is network of queues. Thanks, everyone.
When can we expect to see the next homework posted? And when will that be
I've
due?
already given to the TAs day before yesterday. They still have to convert it to the option choices format. So I'll ping them today to do it soon.
Okay. And that would be due
Hopefully,
sometime next week, I'm assuming.
I would still assume sometime this weekend, but I means let's hope sooner than later.
Okay. Sounds good. Thank you.
Thank you.
Thank you. Thank you. Thank you.
Recording stopped.